Uh, so let me see. I already derailed a little bit, but okay. So I'm going to go over the subject of this presentation momentarily. Go over what digital twin technology is, what blockage detection is, why it's important, and how you can accomplish that through different means. So we'll go through the introduction, background, methodology, and two investigations that me and the team I work with have went over throughout my graduate program here, and I'll finish it off with a conclusion, acknowledgement, and everything. So over my time in graduate school, I have co-authored and authored a couple of papers. Two of the papers, you can see the co-author there, the digital twin modeling for predicting thermal profile, power cables and such. And that is my first taste of sorts of digital twin technology and helped me learn a little bit more. Gary is very knowledgeable on digital twins. He was invaluable to the research that we've been conducting. The other one is real-time thermal simulation for power electronics at the edge. I co-authored this paper with Brandon Pretty, and since he couldn't make it, I gave a presentation on this at the IDETC conference in Washington, D.C. Like a month ago, I believe, or a month and a half ago. I have written one paper, I'm first authored on one paper, digital shadow-based detection of blockage formation in water-cooled power electronics, and I will be presenting this at IMECI in the middle of November next month. Other than that, we're also in the process of I'm being co-authored on a paper about digital twin technology integration in power electronic water-cooled power electronic systems. That journal paper is currently in progress and will be continuing when I leave, hence why I'm co-authored on that paper. So as I stated before, what is a digital twin? Since the simplest definition that I can think of that for a digital twin is essentially it's a virtual representation of a physical test bed. The physical test bed we call PT during this presentation that accurately models the characteristics of this physical test bed in a virtual digital environment and helps to understand the characteristics of this physical system and how it evolves over its lifetime, how it changes as time goes on throughout its initialization all the way to its decommissioning. So what's the usefulness of a digital twin? It allows for rapid and repeatable experiments to give insight into how a physical twin will react under certain scenarios without risking, say, damage to your physical system if you were to perform these on your actual physical system. You could also, it also allows for, say, the monitoring of conditions within the PT or predicting of what the health of the PT may be without, like I said, risking damage to it or expensive experiments or time-consuming experiments, for instance, on the PT. All of this can be done in the DT for much cheaper, reliable, repeatable experiments and such. So this may not be a wholly, completely accurate definition of what a PT may be, but I like to think about an example of what a PT can be as such a, well, if you think about it, Google Maps, the traffic function of Google Maps, this has helped me understand what a PT may be useful for. The traffic monitoring part of Google Maps allows you to see traffic congestion and routes and, well, yes, different, it allows you to see traffic congestion mostly, that's what I'm getting at here, and it can help replan your route. It does this by sampling the GPS signals of users' iPhones if they have one or other smartphones. It can use historical data and sometimes sensors and traffic cameras from the physical system or from the ground, the actual surface, traffic and such. So Traffic would be your physical system, the roads and such, and your digital twin would be Google Maps in this case. Through using the digital twin, you could see areas of high congestion and use that information, or it can help plan a optimal route around traffic conditions. So yes, that I probably didn't explain it too well, but in regard to this slide, building up digital twin isn't just like one go. You can build a digital model, you can build a digital shadow, and like I said, you can build a digital twin. The difference between all of these is essentially how it interacts with the physical system. In a physical model, there's no data transfer between them. It's just a simple simulation slash model of the physical system. In a digital shadow, however, you're getting data transfer from the physical system to the digital replica. In this case, then it becomes a digital shadow. In a digital twin, you have bidirectional data transfer and the ability for the digital twin to directly manipulate the physical system or items within the physical system. Now, how this would work with a digital shadow, as I just mentioned, is you can incorporate an operator. For a digital shadow, this would more often be a human in the loop sort of situation, where in the case of our research, this is where these two graphics are coming from. You're looking at the physical system is giving data to the digital shadow. Digital shadow is giving data or being observed by an operator, and the operator can then make adjustments to the physical twin based on that data. It doesn't have any direct connection to the physical system, the digital shadow. However, with a digital twin, you would have this direct connection between the digital twin and the physical twin, allowing the digital twin to make changes and adjustments and get feedback from the physical to and from the physical system. Oops. So, of course, to have a good physical twin, you have to have, well, if you want a good physical twin system, you have to have good interconnection between the two models. They have to cooperate and respond to inputs the same way that you would see. Say, physical twin in a heating situation, you want your physical twin and digital twin to respond with a characterized and, well, accurate response to temperature. I'm not explaining that too well, but essentially you need to have good cooperation between the two models, or else you won't get accurate simulation within the digital twin model. And so my research has mostly been in the Scepter Lab. This is what the Scepter Lab actually, well, the cooling network for the Scepter Lab looks like in a current, and it's essentially its current implementation. What we will be focusing, however, are DC1 and DC2. These are our DC cabinets, where most of the input to the system is currently occurring from, I mean. Other than that, you've got the extends and batteries and such, but we won't be speaking about that today. So the DC cabinets look like this. And it's a set of DC power converters. There are 6 of them, as you can see, C1 through C6 in sequential order. And the cooling network is featured below it. The cooling network is just a manifold that allows for coolant to be distributed evenly to each of the converters. And we have incorporated thermocouples and flow gauges, or manual, like analog flow gauges, just to gauge the amount of flow going into the system. You can see the manifold here with flow adjustment valves to help readjust and redistribute flow to keep a balance to flow, keep an equal balance to flow to each module, essentially. So in the electrical, this is the electrical portion of what the DC cabinets look like. You can see C1 through C6 indicated in this red box. So these converters, some of them act as buck converters and some of them act as boost converters. buck converters essentially take a higher input voltage and lower it to a lower input voltage for powering minor systems within the network. And likewise, boost one would take a lower voltage, increase it or so, and we use that to power more major systems in the process or in the system. During this process, waste heat is converted inside each of these converters, or is created inside each one of these converters. And the converters are water cooled because we had some air cooled ones. We wanted to go with more water cooled because it had a better heat transferability than air cooled. And yes, and water cooled will allow you to be more space efficient. I found this object here, which is a heat sink, which can demonstrate just how much larger air-cooled heat sinks may be versus water-cooled, of course, because of their heat transferability of water versus air. And you can see here's the cooling network for each of the converters inside the system. And this is a simple 3D representation of what the power converter looks like, including the heatsink cooling block that is mounted to it and is helping to dissipate heat from the system. This cooling block is made up of several very small channels, let's see, 3.24 millimeters, and we found out that these channels actually posed a little bit of a problem for blockage formation within them. So, of course, the main aspect of this is just maintaining the amount of coolant flowing through these blocks, these coolant heating blocks, cooling blocks. We need to maintain them at a constant level to maintain temperatures within the power converter. Because if they get above 80 degrees Celsius, they trigger an automatic safety disconnect, or it shuts off power to the converter to protect itself from overheating. About a little over a year ago, we had a bit of trouble with blockages forming within our converter, or our converter 2, in this case C2, on one of the cabinets. It was, for some reason that we later determined the reason of, we encountered a blockage in the C2 converter. You can see the loss of coolant in the bottom figure here, whereas the blocked line is featured is blue, while the other non-blocked lines are neon greens. So what happened was the coolant to the heater ceased and it tripped. So we ended up fixing that just by flushing the system and adding a new filter and changing out our system from tap water to distilled water after it happened again. So sorry. Yes. So this is what set me on the path of my research, essentially, because then I spent the next year studying blockage formations, their effect on systems. Now, because our research is Navy focused, we work with U.S. Navy on this project, Scepter Lab. I forgot to mention, Scepter Lab stands for South Carolina Energy and Power Testbed for Engineering Research. I wanted to incorporate my work in that regard to U.S. Navy ships. So I looked into what sort of Navy ship systems could be water cooled. And here I found that the radar array of this destroyer system, the Arlenbergs, I believe it's their Flight 3 that incorporates this new radar system, it is water cooled. That's the water cooling subsystem. That's where my research is mainly focused into. It's for the maintaining of coolant and coolant flow within this cooling subsystem to maintain optimal operation of the array subsystem, to keep it in working order and working correctly. So the methodology that I wanted to focus my research toward was, how do I determine the presence of a blockage within our converter system or other power electronic systems without using flow meters, essentially. I, well, through which way would I detect a blockage and how would I do that? Now, our system, as you saw earlier on the manifold, did not incorporate flow transmitters on each of the individual cooling loops. We It would have been extremely expensive to incorporate flow meters onto each of those different loops. So I wanted to focus my research on using what we already had, which was thermocouples, temperature transmitters. So that's what I wanted to base my research on. I wanted to use physical twin technology to create a digital representation of our physical system, our power converters, and model uh, the cooling systems of that converter system using uh, model it and detect, say, losses of coolant and blockage detection within that system simply using the temperature change before and after the convert using thermocouples. Now, the question is, as I've already partially explained, the expense portion of it, why would you want to use a thermocouple rather than just a flow transmitter to help diagnose loss of coolant within a converter? Essentially, as I've already mentioned, the expense part of using a thermocouple compared to a flow transmitter, there's also the aspect of retrofitting systems to incorporate flow transmitters. That is extremely extensive. It's an extensive rebuild. It could involve extensive rebuilds of systems, and some systems just wouldn't allow for it due to space restrictions. And there's also the aspect of maintenance. On a test bed that we have constructed, we've incorporated a couple of these turbine flow transmitters, which is, I would say, the most common type of flow transmitter you can buy, at least for the price. And in these flow transmitters, the turbine styles, of course, they have a tendency to pick up debris and become jammed. Every time that happens, you have to take it out of the system and remove the blockage inside of it. That is blocking that turbine rotor there from spinning and sending signals. Now, with a thermocouple, it's extremely simple to perform this maintenance, and thermocouples or thermosistors, if you wish to use those, can be more easily maintained, and as I said, they're cheaper. Now, my first foray into digital twin technology was creating a digital shadow. Digital shadow, as I mentioned earlier, only has data transfer from the physical system to the digital system, the digital shadow, and no data transfer, vice versa. Yeah. So this paper, which, as I mentioned, will be presented at IMEC in the coming month, is digital shadow-based detection of blockage formation, vertical electronics. We created a digital model or a digital simulation representation in Simscape, MATLAB Simscape. It was the easiest method that we could go about this in. We used the DC cabinet's power converter system and modeled it within this program, within MATLAB, and we characterized this system so that it would follow the same thermal behavior when you reduce coolant to a module. Um, it would follow the same thermal behavior as the physical system. You can see manual flow needles, thermocouples, and the centrifugal pump reservoir tank. If you observed earlier, the cooling system of our entire lab was also in play in the simulation. However, it's not represented because trying to model all of the different components within the system would be far too computational heavy. Instead, we simply modeled the suspected heat transfer or heat loss that the rest of the system would be seeing and used it. We incorporated that system into a simple, I believe, just in the pipe here, to model the heat loss through that ability. So the whole goal of this system, as I said, was to model the thermal behavior of the system. And we could use that to compare it to what we're seeing in the physical system and use that to determine if there's abnormal heat behaviors, which might be indicative of a blockage formation. Now, this is how the digital shadow system and the physical twin would operate, with information coming from each of the components within the physical system being gathered into a data package, which is then sent to the digital shadow. Digital shadow then uses this information and, of course, power input to determine the system health status and whether or not a blockage may be forming in the system. Now, like I said, the system has to be characterized and maintain calibration, or else it leads to accuracy drift, and the results we will be seeing from the digital shadow become inaccurate and such. And you can see some of that here. Before the system was characterized, or before that we manipulated items within the simulation based on experiments that we did in the physical system, we were seeing inaccurate results from that. You can see in red are the simulated rise in temperature for a simulated blockage versus what was actually seen during our characterization tests in the gray there. So now I should explain that our tests are procedure essentially. For our characterization test, we had a couple of the converters on, converter 1, 3, and 4. Each one of these were receiving a certain amount of power input, and they were producing a certain amount of waste heat that was being dissipated into water by convection, of course. So converters 1, 3, and 4 were acting as their controls, and we were performing the characterization experiment on converter 2. Converter 5 and 6 weren't active at this time due to power balancing. So each one of these tests took about 5 hours before the entire system would reach a semi-steady state. Semi-steady state, as you can see, it hasn't reached steady state there, but it's more quasi. If we kept going, it would have reached it. So each one of these tests would start off at the valve for corresponding to C2 converter would be fully open, and then we would run the system until it reaches steady state. You see results on 100% valve position. And then we would run another experiment decreasing that valve position by 12.5%, theoretically, since it's a needle valve, decreasing the flow to the power converters by, again, 12.5%. We would continuously do this for each test, and I have 3 of the tests up there, so 100, 25, 12.5, just so you don't get overloaded from that information. But at the moment, they're inaccurate, the results. However, once we perform characterization calibration of the model, changing parameters within the simulation until it matched the physical system, it produced better results. Now, it became an accurate simulation of our system. Now our digital shadow is calibrated, essentially. So using the information from here, and if you are using a human in the loop system, because we didn't have any automatic way of detecting blockages or abnormal heat behavior yet, an operator could observe this information data flow and use that to determine if there's an abnormal loss of coolant within one of the converters or multiple of the converters. Of course, the problem with this is you always need an operator observe them. So that brings us to the next step, which is creating a digital twin of our system that incorporates automatic data blockage detection and such. Detection of blockage formations within water-cooled electronics using digital twins. We ended up miniaturizing the system, and we created a physical testbed called the BDPD, Blockage Detection and Power Distribution Testbed. So it incorporates essentially the same systems you could see on the larger testbeds. It has the heaters, which are just little heat exchangers with a heater block on it. the pump tank and such, manifolds, thermocouples. We got a couple of flow transmitters on there just for the initial flow balancing and such. That's what the whole pump was using. The turbines came from. These kept getting clogged. And here is a photo of the actual test bed with the different power converters and all the different components that I've just talked to you about. Our digital twin is running on that C-RIA device in the top left. And here is a control panel for our digital twin, physical twin test bed. You can see a real-time monitoring system for the system, for the physical system. Temperatures at different points, the flow to each one, just to make sure it was all balanced, and such like that. In the top left is the information that will be coming from the digital twin. It allows you to determine if it will automatically display if there's a blockage or a suspected blockage or overheating warnings coming from one or more of these heaters. Now, I mentioned automatic detection of blockages. This was done by using a set of checks here, where you would input a set of parameters, say waste heat or waste disposition, and send them into the physical twin and the digital. At the current moment, well, yes, you would then, once you send in this heating parameter and you calculate what temperature of the coolant or each of the converters that you're seeing, or the heater blocks I mean, within the physical system, the real-time transient model. Well, inside the digital twin, there's two different models. You got the real-time transient model, which just models the physical system in real time, subject to changes as it progresses in time. And you also have the steady-state temperature model, which essentially just gives you the highest expected temperature that the coolant or heater block will attain based on the heat input that you have set it to. But each one of our 5 checks, the first two being over temperature checks. So if the temperature that you're seeing within a given time is above what should be by a certain amount here, if it's heating faster, or no, if it's at a higher temperature at a certain time frame, yeah, sorry, 0.25, 0.5, it gives a warning there. If it's heating too quickly or cooling too quickly, in that case, you would see a higher DT or lower DT, and that's also a check. The 4th and 5th check is, well, the 4th one is, are you seeing a decrease in temperature within the other converters? The theory behind this is, well, let me explain. So if you're seeing a decrease in temperature within the neighboring modules that you suspect that a blockage is occurring with, so you would normally see the flow that would be going to the block module is now being redistributed out to the other modules. So with the increased flow to those modules, you would see an increased heat transfer from those modules, and thus a decrease in the temperature. You could use this knowledge to determine which one of the modules has potentially developed a blockage. And the last one is just a number of other over temperature comparison, as I explained. It just uses thermodynamic heating equations just to determine what the maximum possible temperature you would get in your coolant based on your heat input. This is, of course, assuming that the coolant has maintained its integrity or flow. And if it hasn't, you'll see an over temperature in this case. That's also one of our checks. So if all of these checks have been exceeded or activated, it sends a signal to the operator or the system, which can manipulate the physical twin system, that yes, a blockage has occurred. And as I mentioned, with the changes in cooling or heating characteristics between the blocked and unblocked system, you can see how in a heating scenario, the change in temperature within the blocked block essentially will be much higher, and you also see a higher steady state temperature in that block. At cooling block. Whereas in a cooling situation, it's vice versa. You see a slower change in temperature and still a higher steady state temperature. And here is that check, which I told you about the heating from the other converters. You would see a dip in the temperature, for a momentary dip in the temperature, in the other unblocked, supposedly unblocked converters, compared to the potentially blocked converter, because of the flow being redistributed to each of these converters. And how our digital twin, physical twin system would interact in this case is likewise. It's fairly similar to the digital shadow system. However, it incorporates an automatic decision maker which can manipulate aspects of our physical twin, be this power distribution or flow distribution in this case. If you have to maintain operational capacity of a system, say your power converters, if one of your power converters has become blocked, you can take the power input that goes to that one converter and split it off to other converters to help redistribute the power load off those. And you can then redistribute the coolant to account for that increased power in the other converters. Now, I should mention that at the current moment, our physical system is acting more as a digital shadow system, because at the time that this presentation was made, we hadn't been able to incorporate an automatic system where the digital twin could manipulate the digital shadow. So, sorry, the physical twin. And here is the real-time transient model of our system. It's essentially a similar model to what you saw in the last paper that I showed with the DC cabinet, essentially. So here you can see all the different components. Because we didn't have such a large amount of unaccounted for components in our system, characterizing this system is much easier than that system. You don't need to run as long experiments or as rigorous experiments. You get much more accurate characterization this way. Now, yes, like that. So for our checks, how we compare the temperature from the physical system and the digital system is through all of these comparison blocks. Whereas you would gather temperature from your physical system and send it into these comparison blocks, which would then compare it to the transient model and in the absolute temperature model, the steady state model. If there is if there's a discrepancy between these, it would of course send it to this model. And if it trips, or back to the other model, and if it trips that signal, or if it trips the threshold, it would send like a thumbs up signal, essentially, to this system here. And what this system does is it essentially gathers all of the over temperature or threshold checks, and if all 5 of them have been cleared or activated, it would send a overheating / blockage detection warning to the operator. However, you need all 5 of them to activate before it sends that signal. That's why we used an AND gate here. Now, to make sure that this system actually works, we performed a couple of experiments, simulated experiments in this case, using 3 different test profiles. Test profile 1 is we induced a 98.5% blockage within heating block 1. Second one, we induced that same blockage profile in heater block 2, just to make sure that the first one and the second one actually reacted in the same way. And then we induced in the second one, there's also a cooling behavior, just to make sure it works with cooling as well with heating. And in test profile 3, we induced a blockage within 2 of the converters at once to make sure that they both would get flagged and a blockage would get detected. So here is test profile 1, and at the orange vertical line, that's when the blockage was induced. You can see, and if you see, with the blue there, it was induced in heating block 1, represented by the blue dotted line. Immediately after the blockage was induced, we saw a substantial rise in temperature up to the 80-degree threshold, where then the converter was shut down for safety. And after which then the temperature would decrease, of course, because no more power is being fed to it. Now, we wanted to detect this blockage occurring and potentially perform actions to mitigate it before the cooling block or the converter, the emulated converter essentially, reaches this point. So using our digital twin system, it can, well, let's see. It can detect the presence of a blockage well before the temperature in the converter reaches the dangerous 80-degree Celsius threshold. So in the case of here, let's see. Yes, okay. In the case of this, it was able to detect it about 1.33 minutes after blockage was reduced. However, the time to the blockage or electrical power failure in the converter here was about 5 minutes. You have a few minutes to spare to perform maintenance or mitigate the potential damage to the converter. And here you can see it as well. Whereas you can see where it was induced and how close afterwards the blockage was detected versus how long it took it to, well, in this case, it doesn't actually reach the 80-degree mark just because it was in cooling paper at that time. Whereas you can still see that there's a substantial temperature rise in the block here. And the digital twin automatically detects this and sends a blockage warning to the operator. And in the last scenario, you can see a similar situation where it's in each of the blocks, you see that increase in temperature again, and the system can detect that increase in temperature by using all the checks that I've mentioned and send a warning to the operator, essentially saying that there is a blockage in this network. So what I've talked about here is basically the building blocks of building a system that can detect blockages within a water-cooled power electronic system. Now, there's still plenty of work to be done. With this, we need to incorporate a automatic recalibration model or recalibrating feature for our model, perhaps incorporating particle swarm optimization that can update or recalibrate our digital twin system to maintain accuracy with our physical system. We also need to incorporate, say, a digital twin of the electrical side of our system just to inquire with our system to see if the increase in temperature within our potential block is due to, say, an increase in power, an unexpected increase in power, or if it is indeed something wrong with our coolant or the flow of our coolant within the system. And yes, and we're still working on incorporating the actual automatic changes that the digital twin can apply to the physical twin, how it can interact and change systems within the physical twin to help mitigate our blockage scenario. And here's a diagram of how the electrical thermal digital twin is what we're calling it will function with the physical twin sending data to both the electrical digital and thermal digital twin, and based on the results from each of these can help determine system operational conditions. That's essentially the end of my presentation, but I wanted to give acknowledgement to everyone I've worked with in my undergrad and graduate research, especially to Dr. Downey, Dr. Khan, with my advisors, their guidance and such throughout my time here. I also wanted to thank Jack and Carrie for helping me all the time in the lab and just the knowledge they've given me. And of course, I gotta thank everybody I worked with, all the different teams and everybody in those teams that have helped me over the years and collaborated with me. Um, my research wouldn't have been able to have been done without all the help I've been given. And that's the end of my presentation. I hope it went well.